Log on, tune in, find out. Another good idea from Cambridge.
Distributions on random functions for nonlinear regression, please. Kind of?
Kind of.
Okay, I might have promised too little or too much.
Too much. Okay, so thank you, Peter, for the invitation to present here. It's been a really enjoyable week, and yeah, thank you for this. So I'm going to be talking about functional uniform prior distributions for nonlinear regression, and I should say that most of this work was done while I was still a postdoc at University of Dortmund. And so let's get started. Yeah. So I will start my presentation with some motivation for why you might think functional uniform priors might be useful. Then I will introduce these prior distributions. Finally, I will come back in the application section to the example that I have introduced at the beginning. So I think this slide is somehow superfluous in this room. So in nonlinear models, the Fisher information matrix depends on unknown parameters. And typically, of course, the design criterion that you then choose for your optimal design also depends on the unknown parameters. And hence, every experimental that you design, that you calculate, will be conditional on this theta value that you have selected for optimization. So all of the designs are only locally optimal. So in practice, of course, you do not really know the parameters, so you have to, in some kind of way, deal with the uncertainty in the parameter. So there are a variety of options, I think, in the optimal design literature. And one option is then to use a Bayesian approach. So instead of optimizing just the design criterion, optimizing of an average design criterion averaged with respect to a prior. So this is fine as long as you really have a prior distribution. That means as long as you have a properly elicited prior. And I think yesterday in Peter Thal's talk, we saw a really nice example on how one could approach this problem. Or you might have a prior based on historical data from earlier trials, for example, in the clinical trial setting. But what can you do if you do not really have any prior distribution available? So the problem here is that the traditional non-informative prior distribution that you have in the Bayes theory, for example, the Jeffreys prior or the reference priors, they cannot really be used because they depend on the experimental design, and that's actually what we want to calculate in the optimal design problem. So what is relatively often done, I think, or I've seen it frequently in the literature, that people assume some compact set of the parameter space and then use an uniform prior on this compact set. And my point here is that this is, of course, crucially depending on the parameterization that you choose for your nonlinear model. So if you choose another parameterization, you might end up with a completely different optimal experimental design, and in addition, it is usually also quite sensitive to the bounds that you select. So uniform prior distributions on the parameter space are often much more informative than you might expect, especially if it's in a nonlinear setting. So this is the first motivation. The second one is using a data set. So this is a data set from the dose finding package, a dose response trial for 369 patients and 5 treatment arms. The endpoint, so placebo and 4 active doses. The endpoint was a change from baseline in a pain score. So larger value correspond to less pain. And assume that we use a Emacs model to analyze the data. So we have a homoscedastic normal distribution, and the mean is given by an Emacs model, so fairly simple situation. Now I know that there have been I think at least 2 introductions to the Emacs model in the first 2 days, but let me give another one. So the Emacs model has 3 parameters, E0, Emax, and ED50. the E0 is the placebo response. E0 plus Emax is a response that you achieve if you go with your dose, let's say the asymptotic maximum effect. And the ED50 is the dose, so that gives 50% of this asymptotic maximum effect. So a 3-parameter model. And essentially the only nonlinear parameter in this model is the ED50 parameter. All the others are linear parameters. So in this plot, I'm showing the different shapes that an Emax model, so the simple Emax model can take. So it can take reasonably, so it can increase very quickly towards this asymptote. And then if you increase the ED50 value, it slowly converges towards something like a linear increase. And you see that if you look on the parameter value, so this is a parameter 0.1, then this is 0.5, 1.2, and so it's at the beginning it's converging very very quickly, but then it's somehow the convergence towards the linear gets slower. Now, if you assume this model for the data set that I've mentioned, and we use just flat priors for those linear parameters and a uniform prior on the interval 0 to 6, we end up with this fit. So the black dots are the means from this from the raw data, and this is a fitted curve with the credible regions. And you can see that the first side it might look plausible, but if you look closer, you see that for example, this point is not particularly fitted well. Also, these 2 points, despite the fact that the data actually almost look perfectly like a linear, like an Emax model. And part of the problem in this case actually is that this uniform prior here, going from 0 to 6, is essentially already a quite informative prior distribution, because you're essentially saying, well, I believe in a linear shape. So if you remember, this is the maximum dose, and 6 is somewhere here. So this is a problem in this case. And if you increase this upper bound, so you might think you make your prior less informative, you actually make it even more informative, because you're concentrating even more prior probability mass on these linear shapes. Yeah, this is essentially what I said. So uniform priors can be much more informative than you might expect, especially if the parameter is nonlinear, and particularly if you have a low signal-to-noise ratio. And this is part of the problem in this case. So despite the fact that we had 369 patients in this trial, the variability was quite large, and this causes that the likelihood is not particularly informative in this case, and the whole problem is sensitive to the prior distribution. Now, in this case, you could use a Jeffreys prior, but there you have like the slight methodological disadvantage that if you would analyze the data sequentially and use the Jeffreys prior only for the whole first cohort, or if you use the Jeffreys prior at the end of the trial, you might end up with different results, because especially if the dose allocation changed during the trial, because Jeffreys prior is violating the likelihood principle. So just to sum up the motivation, both of these priors are not perfectly suitable for the problems that I've shown. They either depend on the parameterization or the bounds that you select, and the Jeffreys prior has a problem that you cannot really state it completely before data collection, because if you have an experimental design that changes during the trial, you cannot really state it before you start the trial. Before I start, I should say, of course, if you have experience with these nonlinear models, you might come up with reasonably good weakly informative prior distribution from experience or from experimentation or from simulation studies. But what I would like to attempt in this talk is more of a systematic approach. Okay, before starting with the real theory, let's have a look at an even simpler nonlinear model. I think it's probably the simplest nonlinear regression model that you can imagine. So the exponential of minus theta x. So the function looks like this if theta is 0, and then it slowly converges to something like that goes directly down from 1 to 0. And if you look at this, if you a practical problem, you could see like values of theta equal to 0 and theta to 5 essentially cover everything that you want to cover with this regression model. Now if you use a uniform prior on this interval, you see that, or actually what you see here, these are the, this is the 10% quantile, the 20% quantile, 30% quantile, and so on, of a uniform prior distribution. So again, you have this issue that with a uniform prior on the parameter scale, you get an extremely informative prior in this functional scale. So what we would like to have ideally is something that would look like this, that would have the 10% quantile here, 20% quantile here, so that you would have a uniform distribution on the function scale. And that's the main idea. Somehow we will try to, or I will try to, induce a uniform distribution in the space of function. And the nice thing then will be that this will not depend on the chosen parameterization, because we are keeping this uniform distribution in the function space fixed, and no matter what parameterization you will use, it doesn't really matter. Okay, so what's the general approach? The idea is to use some bijective function and then map it into some metric space, where this metric space defines an adequate notion of distance between the parameters, and the word adequate, of course, we'll see what I mean by that. And in this metric space, then you derive a uniform distribution and then transform this back to the theta scale. So in the exponential regression example, for example, it might make sense to measure the distance between the parameters by the distance between the functions here, instead of the distance between the original parameter values. But the problem obviously is, how can I define a uniform distribution in a general metric space? And I was fortunate that people already thought about this problem and came up with a solution essentially, so I just needed to look in those papers. Dembski derives uniform prior distribution on general metric spaces, and then this article by Gozal, it's actually used for these uniform prior distributions are actually used for non-parametric Bayesian inference already. So my approach is only in a finite dimensional setting, but still I think it's a nice approach, so I'm going to discuss it here. So what does he do? The essential idea is that he uses an epsilon lattice. That means he uses a point set, where for each point, all the points in this set have at least a distance of epsilon, and the addition of any point to the set as epsilon destroys this property. In addition, the set needs to have maximum possible cardinality. That means somehow the points in this set needs to be as densely as possible, subject to this condition. And what he uses then is that he uses a discrete uniform distribution on these points in this set, and defines the uniform probability, the limit of this discrete uniform probability distribution when epsilon converges to 0. So this obviously involves much more mathematics that I'm going to talk about here, but the essential idea is that you use an equally spaced grid of your parameters, where the notion of what is equally spaced depends on this metric space that you use. So in the exponential regression example, one could, for example, use just the L2 distance and then choose the points in this set in a way so that the function are each epsilon apart. So let me use a table. So the essential idea is to, in this one-dimensional setting, you could start maybe with this one and then choose the next function, so that these two functions are epsilon apart, and this one is again epsilon apart, this one is epsilon apart, and then so on, and then make epsilon smaller and smaller and smaller, and at some point you will and when taking the limit you end up with a continuous distribution. Now obviously this type of approach can only be done if you are in a one-dimensional setting. So constructing this thing is, I think, computationally extremely hard, but you can actually do something quite simple. So in these two papers, it's actually presented. So if you can approach in the finite dimensional case, if you can approximate your metric by this locally Euclidean approximation, it can be shown that the uniform distribution in terms of theta is given just by the, or is proportional just to the square root of the determinant of this matrix here that, that's in this Euclidean distance that actually changes for each parameter theta 0. So it's a quite familiar formula actually if you think of it. And you can see that this is not the only approach how to derive this. There are other approaches on how you actually come to this formula. Okay, there are a lot of special cases that one is familiar with. For example, if you just have functions from Rp to Rp and you use the Euclidean matrix in both spaces, this is nothing else than the traditional change of variables theorem. So if you have that's something that's also quite frequently done, that you say I choose my prior distribution in a way that it's uniform in a certain parameter transformation, and this is exactly, and then you use the change of variables theorem, and this is just a special case of this more general result by the other authors. And another special case is actually Jeffreys prior distribution. So if you choose by M the space of residual densities, and you choose as a metric the empirical Hellinger distance or the Kullberg-Leibert divergence, you just obtain Jeffreys prior distribution, and in this way it can be seen as a reasonable default prior distribution, because it's, in this sense, it is a uniform distribution on the space of residual densities. But it is conditional on covariates, and that's the main difference to what I'm talking about here. Now, in the case of nonlinear regression, as I said, one reasonable distance is just this L2 distance, and you can, by making a local linear approximation, you can just approximate it by this type of formula, and then finally obtain a formula for the uniform distribution, the square root of the determinant of this matrix Z star, where Z star is the integral of this. And this again looks quite familiar, because this is if you have a normal distribution and homoscedastic variance, this is essentially the Fisher information but integrated with respect to a uniform distribution of the x. In the linear regression setting, you obtain a prior distribution that's just constant, because this derivative here does not depend on the thetas, which is the familiar distribution that you would use in a linear regression. Okay, coming back to the exponential regression example, you can calculate, you can do all the calculations, you end up with this distribution, and if you plot the quantiles, so this is the 10%, 20%, 30% quantile and so on, you see that this really uniformly covers the space of functional shapes, and you can see that this is a rather non-uniform distribution on the theta scale. So here it looks exactly as the thing that we wanted to achieve in the first place. Of course, calculation of this prior distribution is not really trivial. Also, Jeffreys prior is not really, in some cases, not really trivial to calculate. But an advantage here is that you only need to calculate it once, and once you have done that, you can transfer it, or you can approximate it and transfer it to the desired situation. That means the desired design region, the desired parameter bounds. Yeah, and one approach that I think would be crucial for practical application is that you approximate it in terms of some known distribution, for example, mixtures, and then you can use it, for example, in Winbugs or other computer code. Okay. So let's come back to the dose-response study. In this case, you remember we just had one nonlinear parameter, and I will only use this functional uniform prior for this one nonlinear parameter, so on this space, I will assume the same bounds. If you do all the calculations, you end up with this prior distribution, and the posterior credibility bands look, at least for me, so here you can see the functional uniform prior. For me, they look a little bit more reasonable than when using the uniform prior distribution. Particularly, you can see here, first of all, the posterior median is somehow closer to the observed data, and the uncertainty intervals in this region is a bit larger, which I find quite reasonable, because this is where the action takes place in this curve, and so there should be most of the uncertainty. And the functional uniform distribution exactly leads to this behavior. So in this setting, I think functional uniform distribution makes sense. Okay, so what I did as well was a small simulation study. So the simulation were performed actually in the setup of the Pharma Adaptive Dose Ranging Working Group, the second round led by Vlad. And I used, the setup was, there was a placebo dose and then 4 active doses, and I used 25 or 50 patients per group with a standard deviation of square root of 4.5. In this case, I used not the standard Emax model, but the sigmoid Emax model, which has one additional parameter here, the theta 4, which essentially determines how steep the curve is. So one additional parameter to estimate, and I only used again the functional uniform distribution on this nonlinear part of the function, and I used bounds for both parameters. So these were the functions that I simulated from. So I had 3 sigmoid Emax functions, and then 1 linear function and a quadratic function, just to see how well the priors work in case of misspecification of the model. And what you see here is the estimation error for the 2 prior distributions, and probably the interesting thing is here that for the linear parameters, so theta 1 and theta 2, you get roughly equal estimation error, but you can see that for the nonlinear parameters, the functional uniform prior leads to a smaller estimation error, which makes sense because, the uniform prior actually might be an informative prior distribution on the shape space, leading to a kind of a bias in these parameters. If you look at the estimation of the dose response function, you see as well, so the MAE is a mean absolute estimation error. You see that the functional uniform prior performs better in most of the cases. Actually, for the sigmoid Emax 3, uniform prior is a little bit better. But this might be due to the fact that obviously the uniform prior is centering or is favoring certain shapes, and this might be one of the shapes that the uniform prior simply favored. And obviously then it will, this model will perform better in this case. But otherwise, estimation error is smaller for the functional uniform prior. CP here is the simulated confidence level. So I calculated credibility bands for the estimated curve, 90% credibility bands, and I looked how often those actually covered the true value. And you can see that it's roughly at the level that you would expect, 90%, maybe apart from the quadratic model where it's a little bit smaller than 90%, but both of these priors led to a quite good coverage. And the last column here, it's the interval length, so the average length of the confidence or the credibility interval, and you can see that the functional uniform prior leads to a shorter credibility interval length, but has the same or an even larger confidence coverage probability, which is I think a nice property from the frequentist perspective. I also looked at other simulations, for example, for binary data. I also compared it to the Jeffreys prior, and in this case, the functional uniform and the Jeffreys prior performed roughly equally well, but they both perform better than the uniform prior distribution. So this is the last example. What I did, I calculated an optimal design for this exponential regression model. So in this case, the Fisher information is given by this formula, and this is proportional to the inverse of the asymptotic variance. And what I did is just to calculate this expression with respect to the uniform and the functional uniform prior distribution. In this optimization, I just looked at the restricted design space, so the x were confined to the space 0, 10, and I only optimized up to 5 design points. Now the Bayesian optimal design, what it does, not the Bayesian, the uniform, the optimal design corresponding to the uniform prior distribution concentrates almost all of its weight at one design point at 0.4, while the optimal design under this functional uniform prior spreads its allocations more in this region between 0 and 10, but it also has one design point that has roughly 50% of the allocations. I think 10 is actually the point that has 50% in this functional uniform prior. Then if you look at the efficiencies plotted, for each of the theta values, I calculated the locally optimal design, and I just look at the efficiency of the two different designs. What you can see here is that if you use the uniform prior distribution, you have a very low efficiency for all these functional shapes, and you only achieve something reasonable here, here, and here. I think here the efficiency is maybe in this region maybe 0.9, whereas the functional uniform prior distribution performs well up to here maybe. Actually, I was a little bit disappointed yesterday when I calculated this. So the performance really deteriorated in this region. I hoped it would look a little bit uniformly good, but this was not the case, obviously. But still, I think it's performing quite well for most of the shapes, whereas the uniform prior distribution only works well in this region. Okay. So the main points for me here is that these functional uniform priors avoid some of the problems of the Jeffreys prior and priors that are uniform in the parameter space. First of all, they are parameterization invariant, and they are available before you collect any data. So if you calculate your optimal design, I mean, you do not have any data to come up with a Jeffreys prior. They are not really motivated by any information theoretic considerations. That means there's not really a reason to call them formally non-informative, although they are obviously quite similar to non-informative distributions. But essentially, the selection of this space where you enforce this uniform distribution is up to the user. So yeah, the most I could call them is reasonable. I think in this nonlinear regression setting, if you use a certain nonlinear model, then you believe that one of the shapes is the true one, but which one is the true one you don't really know. So I think it's a reasonable assumption for nonlinear regression. And I would also like to mention that obviously there are situations where this is not adequate. First of all, in the situation where you have something well justified, a well justified prior, of course, but also if you have like a very flexible nonlinear model, you might not really want to cover all of the shapes. For example, in neural network models, you might want to penalize towards smooth functions and not really cover all of the function space that the model is really, or the model the model can produce. And yeah, that's it.
Any comments? Peter?
Well, this looks like wonderfully useful stuff for the practice of Bayesian inference, especially in small samples. And I want to use it, but I couldn't figure out exactly what you were doing. So it seems that once I got the idea and I thought, oh good, now we're going to see how he derives these magical priors that are so nice, suddenly it seemed like you pulled a rabbit out of a hat.
Yeah, you only told us you only defined it like in the limit, but you never told us how you actually work with it, right?
Maybe I was a bit quick on this slide.
Well, we haven't half passed, did we?
Sorry?
This may take a time. According to the program, we have until half past.
So you can
But
go
we have a lot of
slowly
time.
on
Okay,
it.
okay.
You can show your
Okay.
longer version of the talk, if Sergeant.
Explain it.
Yes, that's right. Yes.
Okay, so so what I do for nonlinear, or what I propose for nonlinear regression, is that you use this type of metric, so the L2 distance, and you can actually approximate this matrix by doing a local linear approximation to this function mu, as long as it's differentiable, and then you can write this approximation of this metric in this form. And this is essentially what we need for applying this theorem. So this is exactly the same form as here.
That's
Still
where the
too
V
fast,
came
go back.
from. The V is,
Too fast.
so the V is, go back to the.
Yeah, what is V?
The
V
V is
looks like magic.
J transpose J? Yes.
What the V?
Yeah, what's
No,
V?
it's integral.
Where does V come from? V is a magical object. Where do you get it?
Ah, the V.
Yes,
Yeah, the V here is this.
yes, J transpose J.
It's first order approximation of nonlinear models.
Take the derivative vector
Yeah,
and then take what, the outer product?
yeah,
And that's V.
yeah. In this case, that's V. Yeah.
Just first order approximation of a
We got a
nonlinear.
paper on this, right?
Not yet.
You put a V on the slide before it's lodged in the...
In the equation.
There's no V in the equation, so that's why I think we're confused, because there's a V on the next slide, but it's not defined.
Okay. Yeah.
Well, if I
Should that be J transpose?
Yeah, depending on if J is a row or a column vector. Yeah.
And how do you get previous expression, the one with V?
that's a theoretical paper saying that.
No, this is just if you have your metric, then you make for example, if you take the square of it and make a Taylor approximation, that would be one way
Yeah,
of.
but how do you get P from that?
He gives references there. He said Pinnock gets it
P-
in the 2006 paper. He tells you how to get it, and you have a different way, right?
I think that's a general theorem. And if you can have a shape like that, then you can find
How
the
do I
general
get
theorem.
this? Yeah.
And then he's saying,
This is
I
difficult.
can use that general theorem,
Yeah.
taking V as the Jacobian and so on. So
And you
yes,
standardize it so you have a.
yes, so
a
that's general theorems.
Yeah.
And
Actually, I didn't really
to
talk
apply
about.
the general theorem.
Yeah.
Okay.
Can you give some hints on how you get P from
Oh.
this stuff?
No, actually, that was really done in these papers. I mean, they didn't do it for this type of expression, but it's really just a minor step from what I did to what Gozal did in this
Can you explain
1997.
intuitively why the magical prior is the square root of the determinant of V normalized? It's just it's like from the sky. I don't have any idea.
Yeah, it's
That's the
difficult.
bottom line.
Well, for
That's
nonlinear
like
models,
change it.
volume of the ball.
Yeah.
for the nonlinear
Yeah.
models, that's
local
It's-
volume of the ball and the dimensions.
It's difficult to give an intuitive notion, at least for me.
Yeah, but why it's square root? It should
Well, then he
be
takes the
root
square
of 1 over m,
The,
where m dimension.
right.
no, the square root comes just from the
Something
square
like
root
that,
here.
It will be error.
The square root comes just from the square root here, I think, if I remember correctly.
Well, so go back to where does that, why are you taking the square root in a high dimensional space? Where does that come from?
In this,
Yeah, go back. Is it on the previous slide? Yeah.
Just
So you
the
take
L2
the
distance.
because I square here, then I take the square root of the integral. For me, it makes sense.
Chris, and then look.
So is theta a point, not a vector?
In this case, theta is just a point, yeah.
One dimension.
But you integrate with respect to the x, not with respect to the theta.
I'd like to say, I mean, this looks really nice, you've couched everything in for the objective of getting something that's non-informative, but I think this tool looks much more broadly applicative. And thinking about Bayes' optimal design, the prior's got at least two different roles. One is when you do the inference, you've got the prior to go with your data. There, you might argue you want to be non-informative because, well, people do, but at the design stage, the role of the prior is coming through because you're saying, I want to average over this set of possible models, and it's where you're putting the weights. And I can't see why you really want to be non-informative there. And you saw in your example, what you'd found was you were good in this region, you're not so good in that. And what you could say is, well, okay, and I think I need to put a bit more weight in that bottom corner. So can you take this prior and say that's the kind of basic starting point, and then put on top of it something that shifts a bit of emphasis, which you couldn't do on any old prior because it's already put 90% of the mass somewhere that you didn't think it was going to be. So I think if you can understand just how to get that basis shape, which is what the other questions are all about, then we've got somewhere we can then put something else on top of, and I think that looks really...
You could be uniform around the centering function, right?
I mean, in a local optimal design, you've gone to one extreme and say, I guess this is the true parameter, I'm going to make everything optimal for that.
It's very good. So
Then if you say, let's be non-informative, you've sort of gone all the other way and say, I've got no idea where I'm looking and I'm going to be optimal in some ridiculous case. What you want is, I'd have thought, here's my guess and this is my uncertainty about it, and I want to be optimal for when the true curve is somewhere in that sort of place. And I think you've got a nice framework for that.
He's blaming you for being a frequentist, yeah? He's blaming you for being a frequentist.
Oh, I'm being a frequentist.
Chris, it means that it's a very nice way how to pick up prior to please a master or the master.
To please Joseph Bernardo, but I mean, to do what Peter was doing, you got a very informative prior yesterday.
He had a very informative centering. The prior was not informative, and that's where Bjoern could kick in. He can center it around that centering and then say uniform within a certain neighborhood, right? Which can be wide one. Look.
Yes. On your last examples, it seems that you would have preferred to have the efficiency approximately uniform over all the place. But the way to do that is to use a minimax approach or to put some LP norm on your efficiency, not considering the expected efficiency, but the expected LP norm.
I have one more request. You can't do this instantly, but the next time you give this talk, if you would draw pictures of the prior for each parameter. You got the foolish uniform priors, then get the magical priors of theta 1, theta 2, and so on. That you can actually draw pictures of, and then the prior for the function of dose for each of several doses. I would love to see what those look like.
Beat in France.
It was also about the centering.
Okay.
My question was about the last example also. I would have liked to see the designs because you just say so you don't have a slide with the designs.
No.
And my
but I can tell you.
You've tried normal priors because usually we use all log normal priors for theta and see which one would be to see whether we will gain a lot by this.
Yeah, but how should
because uniform priors, you know that bad. Well.
Uniform not on the right thing.
When in Bayesian, we will not use uniform prior for this nonlinear parameters anyway.
Yeah, but I've seen it more than once, so.
It's a very common pitfall to put the uniform and logistic parameters. What you get is a highly
that's what we know. It's not good.
So you know that.
For nonlinear models,
yeah, probably the person in this room know, but I think there are some.
No, I think it's common. Please.
Could you go to slide number 20?
But it would be interesting to compare.
Slide number 20.
So the one on the right, it looks uniform in that space. But is that space the biologically interesting space? As you said, all the action is happening down at the left. And there, if you look vertically, there's enormous gaps between the bottom curves, but tiny gaps between the top curves. So I have a question whether uniform in that space is actually biologically interesting.
You mean in the dose response to the dose?
It depends on the distance measure. He used L2 norm, so in that sense it's uniform, right?
Yeah, it depends on the application as well, you know. I mean, what you want to achieve with a prior distribution.
Not only the distance, also in there was then hidden like the integration over the x.
Yeah.
Depends on what range you take for the x. Here's replaced one problem by another one.
problem. Yeah.
But it's perhaps an easier one. Yeah. Please.
Two questions. One is really the one that Peter just commented on. The first is what relation this has to measures. There's measures of intrinsic and parameter-based nonlinearity for nonlinear models, and this seems to be very close to the trying to get to an intrinsic measure as opposed to getting to something that has parameter effects nonlinearity. Kind of old work. Doug Bates was around last week, and he's one of the ones who's a primary developer of those, so he probably would have asked about that. And the second was exactly the point that Peter brought up, because of the fact that you have this integration on X, and sort of the same thing that Stephen pointed out. If you look across X, you're trying to get something that sort of balances across X the uniformity. But that depends on what X's you have in. So I would guess that these designs and the measures that you get in the theta space might be fairly sensitive to the range of X's. I'm just wondering if you've explored that at all.
Yeah, I mean Peter was absolutely right. I mean, what measure you use for the x will influence your prior distribution. And actually, I'm not really familiar with these intrinsic measures of nonlinearity. Maybe I need to look into this.
I wouldn't recommend. I don't think there's been much done with it since then, but it goes back about to the 1980s.
But so I think the X range is kind of much easier to pick because it's something related to the problem, yeah? Like in dose ranging, you know what's practicable, yeah?
Yeah, the X range, but not what measure you use for integration. It's not...
Too bad.
So, if I look at this object I missed a few first minutes of your presentation, but if I look at this object integral of squared Jacobians, so it's nothing else as information matrix actually for uniform design.
Yeah, but in the normal distribution, only for the normal distribution with homoscedastic variance, I think.
No, it's an
right?
information matrix for any nonlinear regression if you work with first and second moment. So it's what is coming out. So you actually standardize, it's maybe a good idea to standardize everything by information matrix for uniform design. Because you just do integration along the whole area AX, and density of your design everywhere is the same. So it's uniform, continuous uniform design.
So his definition didn't make use of any assumptions on the residuals, so it can't be the same, right? Like the residuals could be anything.
Residuals, yeah, it's what we do in all the times in linear and non-linear regression. You do not have any assumptions about distribution of epsilon. You just assume that there is
independent.
They're independent. Yeah.
And they need not even be for this notion. I mean, it's kind of perverse in the application.
Yeah, I understand. But I just try to say is that this object is identical if you consider non-linear regression with, say, independent errors and zero means. So then it's information matrix for uniform design. Anybody there from the design community, they should check me. My statement.
No, sounds good.
Oh, it's nice, nice idea.
Rosemary?
Yeah, no, this is a much less technical question. Your example, there was placebo and 4 doses, right?
Mm-hmm.
And you said they were in cohorts. How many cohorts were there?
I didn't say they were in cohorts.
I thought you
4 active doses and placebo? Is that what you mean? Yeah. 4 active doses and placebo.
I thought you said the patients came in cohorts?
No.
Sample sizes are
He said in groups, but I think group was only
the group
patients
size was
assigned to a
50 or
dose.
25.
Yeah, it was very big samples.
So they were all randomized at the same time?
No, I don't really know. I just have the data set. I was not involved in this trial, so...
Some of it was observational data.
Yeah, exactly.
I mean, the purpose of my question is in things like that, if they do come in cohorts, you need to think about fitting a cohort effect. And I don't see any point doing incredibly elaborate stuff if you haven't thought about that basic thing. But if you say maybe it was not even given in the data.
No.
Where is Vlad?
Vlad would know.
Look.
No, that was not an example from our what he showed.
The simulations were. So the simulations were done.
I don't know what Rosemary was asking, the example which you have in your software in those findings, but that's not from our work group.
No.
But if they come in cohorts, you can also adapt the design, which is
So he's not adapting Rosemary. This is like once
nice
done.
use of this.
No, it's not the adapting, it's whether he's actually fitting cohort effects.
No. Because there is no cohort. Everybody is at once allocated.
One more comment, Luke.
Well, I wondered if you try to do the same with binary responses, and if in this case you also get the information matrix for uniform over X.
No, I don't think so. I mean, I'm not an expert in optimal design. That's the problem. But I don't.
But you would do the same thing.
Yeah, I would.
No matter what the sampling model is.
Exactly.
Right? Exactly.
That's the point. And I think the Fisher information for this binary regression model would be different from this one. So
this is why this is a question.
But it will be one multiplier, just one additional, that's all. But probably a good idea.
Thanks for all the comments. We should break for our coffee break. Please come back. We're going to have some really nice stuff coming up. Dose escalation and PKPD. We want to hear. One more less technical point.